Well, welcome to my lecture on hypothesis testing. This is for material in Chapter 8. So your primary hypothesis tests, and usually the very first hypothesis that you see, are concerning the population mean, and that is mu. Okay. So a hypothesis test is a statement about a population parameter. In this case, we're specifying the mean mu. We'll go into examples later where we're dealing with proportions or different values later. You can also do standard deviations. You can do much more complicated hypothesis tests. But for now, we're mainly focusing on the mean. Okay. So one important fact is that the null hypothesis is a statement of equality of H0. So it's usually the mean is equal to 5, is equal to some value, or it's less than or equal to, or greater than or equal to, but it always involves equality. And the null hypothesis is always a statement about the mean being equal to a different value or not equal to the value or greater than a value. Okay. The default, what is assumed to be true, is the null hypothesis in this scenario generally, especially when calculating what's called a type 1 error. And the alternative hypothesis is what needs to be proved. So is there data supporting the alternative hypothesis? So here's an example. An economist believes we have entered a recession and the mean wage of adults 18 and older has decreased from $16.25 an hour. And to test this hypothesis at the 5% significance level, a sample of 30 individuals is taken, and it's found that the sample average is $14.90 an hour with a sample standard deviation with 375. The question is, what can the economist conclude here? Okay, I want to emphasize here that yes, the sample average is $14.90, but the question is that every time you take a sample, there's variability in the result that you'll get. Is there enough variability or not enough variability to conclude that $14.90 is much different from $16.25? Well, to determine that, we're going to calculate a probability concerning our sample. Is it distinctly far away enough from $16.25 that the odds of observing a sample average of $14.90s are so low that we should conclude the alternative is true, that the mean wage has decreased? Or is there not enough? Is it only weak evidence? If you were to take another sample of individuals, maybe you'd get a sample average of $16 an hour, or maybe even more. It all depends on how much variability, how much odds, how much probability you have. Okay, so let's first break this down. So I said our null statement of equality, that $16.25 alternative is what the economist believes, what they want to prove, that it's less than $16.25. Okay, and we're faced with a decision, and there's certain reality about this. So here's some outcomes of hypothesis testing. So this is going to be your decision. Okay, you have to decide fail to reject H0. Okay, and that's the terminology of a statistician, because it's not that we believe that the alternative is true. It's just that we don't have enough evidence to reject the null. Okay. It could be, for example, if we did an extreme example, you have to decide if someone's guilty or innocent of a crime. It could be that you believe that they're guilty of the crime, but there's just no evidence to convict them of it. So in that case, we would fail to reject. Okay. Our other decision is to reject the null hypothesis. But there's always a reality of the situation. This column here indicates the reality of is that H0 is true. Well, if you fail to reject the null hypothesis and H0 is true, well, that's great. You made the right decision. However, if H0 is true and you decide to reject the null hypothesis, that's what we call a type 1 error. And that's a very sad thing, right? In the example of crime, that would mean you've rejected the assumption of innocent. We're assumed to be innocent until proven guilty, and the reality is that they are innocent, but the jury decided to reject the null hypothesis of innocence. They're going away to jail for a long time, even though they didn't commit the crime. That's the type 1 error. That's a sad thing. Okay. Here, this column represents that the alternative hypothesis is true. Okay. Well, if you fail to reject H0, that means you fail to reject that they're innocent, meaning you conclude they are innocent in practical terms. You just don't have all the evidence. And the reality is that the alternative is true, that they committed a crime. Well, then you're letting a guilty person go free. They can commit more crimes. That's a sad thing. That's what we're calling a type 2 error. We fail to reject H0 when the alternative is true. If, however, you decided the alternative is true and you rejected the null hypothesis, then you made the right decision. Okay, so this is our decision matrix. Okay, and those are the possible outcomes. Okay. So when you make decisions in statistics, they're always going to be based on data. The thing that estimates our population mean is the sample average. In fact, we proved that's unbiased. And we would expect a null to be false if the sample average is small in this example. We associate how small the sample average is with a probability, and that if that probability is too small, the data is unlikely to be true, and we reject the null. Okay, we make decisions based on our significance level of alpha, which is called the type 1 error. However, another common thing that we'll make decisions on is the p-value, the probability of observing the data, and that is almost synonymous with alpha and the type 1 error. It is the type 1 error, but it's not quite alpha. Okay, so one important thing that we've already discussed, the t-distribution is given by this. Okay, I also want to recall that if we use, instead of using S, we use the known standard deviation sigma. We will have a normal distribution by the central limit theorem. But in practice, it's common to use the sample standard deviation. Okay. When you make a decision, there are three areas in which three forms of the alternative. So here the alternative is the one that we're dealing with, is that mu is less than some value, in which case you reject H0 for values below the mean in this region, this red region on the top left. If, for example, our alternative was that mu was greater than some average, we'd reject when it's above the mean, the sample average is above the mean, and there's some critical rejection region for the observed value of the mean here. And if it's two-sided, meaning that mu is not equal to some value, well, it can fail this hypothesis if it's too small or if it's too large, and that's depicted on the bottom here. Okay. Now let's get back to our problem. I play a game called Name the Variables, and I've already filled in all the variables. I filled in the null hypothesis, I filled in the sample size, I've filled in degrees of freedom because I'm going to use a t-distribution. I specified S, I picked out the significance level alpha, and I've identified the sample average here. So all of this information from name the variables comes from this problem in which the economists believe we've entered a recession and the mean wage of adults aged 18 and older has decreased from 1625. Well, I've just stated the null and the alternative there. To test this hypothesis at the 5% significance level, that's alpha, a sample of 30, that's n, observations taken, and is found the sample average x bar is 1490 an hour with a sample standard deviation s of 375. Well, we're trying to determine what the economists conclude, so let's go about that. So this is called the critical value method, and we're going to reject the null hypothesis. The odds of observing the data under H0 is less than the critical value of alpha. Remember, the data we observe is based on our average x bar, which estimates our population mean. Okay. So I'm going to calculate the 5% region, and the probability x bar is less than that region has to be equal to 5%. We use the t-distribution here. This is the t-distribution. X bar minus mu divided by sample standard deviation over root n. We saw that in the earlier slide. And I do this to both sides. And I get a t-distribution. And from the t-distribution, I see that the value of minus 1.699 corresponds to a 5% probability. You can confirm that in R or using your table on page 699 of your textbook. Okay, so now I want to determine the region for rejecting the average, for rejecting the null hypothesis based on the average. I set these two quantities equal to each other and solve for R. R is this value. It's 15.2. We observed a sample average of $14.9 an hour, and that's less than the critical value of 15.2. So it's in the rejection region. Hence, we reject the null hypothesis at the 5% significance level. If I had a different level of significance, I might not be able to reject this hypothesis. So your significance level, that 5%, is very important. Okay. Okay. And here's another example. Okay. An exercise scientist believes that in recent time, the mean amount of time spent exercising has changed from 40 minutes a day. To test this claim, a sample average of 49 individuals taken and a sample average of 45 minutes is calculated with a sample standard deviation of 28 minutes. Test this hypothesis at the 5% significance level. What should the scientists conclude? Okay, so the first thing we do, we just name the variables. I have my null hypothesis 40 minutes. The scientist doesn't know how it's changed until they collect the data, so it's mu not equal to 40 minutes. I identify the sample size, my degrees of freedom, the sample standard deviation, my significance level, and x bar. Notice I did alpha over 2 here because this is a two-sided test and my rejection region is going to be two sides. So I need alpha over 2 in this area and alpha over 2 here, and 1 minus alpha goes in the middle. Okay. Okay. So when I test this, the first thing I notice is that it's two-sided, so it's a symmetric region. 5% is the probability x bar is less than minus r or bigger than it, so it's twice the probability x bar is greater than, absolute value of x bar is greater than the positive rejection region. Okay, so I set 2.5% equal to that, just dividing by 2 from the previous line. Then I take the t-distribution, because remember x bar minus mu divided by s over root n is the t-distribution. And I calculate this value, r minus 40, and I set the quantities equal to each other. And I'm going to observe that the rejection region, okay, one thing here is that the absolute value should have gone over here. Okay. And I solve for r, and I obtain this rejection region. So I'm going to reject if x bar is greater than 40.04 minutes or it's less than 31.9 minutes. Okay, since I see it's 45 minutes, there is not enough convincing data to reject the null hypothesis. Notice that this is not in the rejection region. Okay. So it's just a matter of solving the equation here, okay? Okay, here's another example. And this example is slightly more complicated. These are the most standard examples thus far in which you do a calculation on mean, you use x bar, you have the sample standard deviation. But things get more complicated and you have to identify distributions in certain situations. The previous examples are the most common, okay? So in this situation, we know the standard deviation. It says at a local parts company, the mean resistance of a resistor is specified to be 9 ohms. That's specification for this part. Okay, with a known standard deviation of 1.7 ohms. And that 1.7 ohms might be due to company records. That's how they know it. Okay. If you don't have the records, historical records, then you had better use the sample standard deviation. But because it said known standard deviation, I'm going to assume a value of sigma. An engineer believes that the mean resistance of the resistors is less than specification. To verify this contention, a sample of 30 resistors is taken and it's found that the mean resistance is 8.7 ohms. Test the hypothesis at the 5% significance level. So we just name the variables. I state the null, I state the alternative. Industry standard is that it's 9. Engineer believes it's less. Sample size of 30. Standard deviation, I use this symbol. Instead of S, I use population standard deviation of 1.7. Now alpha is 5%. I have the observed sample average. And because I do not need to know alpha over 2 here, because this is a one-sided test. Okay. So one thing that I'm going to notice is that the probability a standard normal z is less than minus 1.645 is 5%. You can use the table on page 697 or the R command to verify this. Now, the central limit theorem states that if I know the standard deviation, this quantity is a standard normal. So this is different than all previous examples because I have a standard normal and not a t-distribution with known standard deviation. So 5%, that's equal to the probability a standard normal is less than 1.645. And if I can replace the standard normal distribution by this quantity by the central limit theorem. So now I just plug in what I know. Under the null hypothesis, the mean is 9. I have 1.7 for the standard deviation. I have the sample size. Then I just solve for x bar. Okay. So when we solve for x bar, I'm going to get 8.48 ohms. Okay. And that's my rejection criteria on the sample average. So our conclusion is that we can reject our null hypothesis if we observe a sample average of 8.48 ohms or less. Okay, now our sample average is not less than the critical value, it's greater than the critical value, and hence we fail to reject the null hypothesis. 8.7 is not in the rejection region. Okay, so this was slightly different from the last example because I used a normal distribution and not a t-distribution, so you had to identify that. Okay, that was how it was different. Okay. Now, in our last examples, our ultimate goal was to determine the critical value, our rejection criteria. This was not given to us in all the previous examples. But in this example, we are given the rejection criteria and we're not given alpha. So alpha, the significance level of our test, is equivalent to determining the rejection region. So in this case, we're not given alpha as we were in the past, but we're given the rejection criteria. So in this example, I'm asking you to calculate the type 1 error, which is known as alpha. So it says that a local parts company, mean resistance of a resistor is specified to be 9 ohms with a known standard deviation of 1.7 ohms. This problem reads very similar. This time the CEO has decided to make a decision. It's decided to reject the null in favor of the alternative if in a random sample of 30 resistors, the average resistance is less than 8.7 ohms. Calculate the probability of a type 1 errors. Okay. And I could have said, is 8.7 ohms or less. Okay. It doesn't make a difference because I have a continuous distribution. Okay. So I'm being asked to calculate the type 1 error. That's alpha. Okay. Probability of a type 1 error means that we reject H0 when H0 is true. I am given the rejection criteria. And it's this. That's my rejection criteria. If in a random sample of 30, the average resistance, so average resistance X bar, less than 8.7, that's my rejection criteria. When mu is 9, when H0 is true. Remember, our null hypothesis is that the mean is 9. So we calculate this via the central limit theorem. Then we calculate z, so we're kind of working backwards from what we've done in the past, and we see that there's a 16.8% chance of a type 1 error. So that would mean that 16.8% of the time, with this decision made by the CEO, not super well informed, that you would reject the null hypothesis. You would conclude that the population mean is less than 9 when in fact it's not. Okay, and that would happen 16.8% of the time. Okay, well, in our slides there was something called a type 2 error, and the problem reads pretty much the same. There's a typo there, that should be 8.7. So here's our rejection criteria. The average resistance is less than 8.7 ohms. Okay, and I'm being asked to calculate the probability of type 2 error if the true population mean mu is 8.8. So type 2 error means fail to reject H0 when the alternative is true. And I'm being told that the alternative mean is 8.8. So mu is 8.8 here. Okay, so I want to calculate probability x bar is less than 8.7 when mu is 8.8. Okay, so this means I apply the central limit theorem, I calculate this quantity. That's the probability of standard normal is less than minus 0.31 is 37%. So that means 37% of the time you would fail to reject, at 37% of the time, you would fail to reject H0 when the alternative is true. So failing to reject H0, that means concluding that the mean is 9 ohms when in fact it's less. That's pretty bad for the customer. And that would happen 37% of the time with this rejection criteria and this value of the alternative. Okay. I want to go through another type 1 error here. So in this instance, an industry requires that the proportion of defective parts be 10% or less. A quality control engineer believes that the population of defective parts produced exceeds this threshold. The engineer decides to reject the null hypothesis if more than one defective is found in a random sample of 10 parts. In this way, the probability of type 1 error is preset to what value? So there's a decides there. That means there's a decision being given. More than one defective part is found in a sample of 10. I wonder if that rings a bell. So X is the number of defective parts out of a random sample of 10. That has to be discrete because we're counting numbers of defective parts. They're independent because it's a random sample, and there's a finite sample size. Well, if we go back to chapter 3 with discrete distributions, this fits a binomial distribution with a sample size of 10, and the probability P is assumed to be 10% under the null hypothesis. So if I want to calculate the type 1 error, well, that means I reject H0 when H0 is true. Rejecting H0 means probability X is greater than 1 when P is equal to 10%. I just calculate the probability of the binomial distribution with n equals 10, P equals 10% is greater than 1. And using R, I can see that that value is 26.3, or I can just calculate it by hand. Either way. Okay, so that's another example of a type 1 error, but the distribution that I use is not always a T. In most instances it is, but I want you to know that there's lots of intricacies in hypothesis testing, and this is one of them. Let's do another example of a type 2 error. So it's the same problem, but now, and the engineer has the same rejection criteria if more than one defective part is found in a random sample of 10. But we're being told in this example, if in fact the probability of a defective part is 15%, meaning the alternative hypothesis is true, because the industry standard, what's believed to be true, is that it's 10% or less. And the alternative would be that it's more than 10%. So in this case, we're specifying that the probability defective is 15%. What is the probability of type 2 error? Well, type 2 error means fail to reject H0 when HA is true. Well, fail to reject H0 means that X is less than or equal to 1. Okay. When the alternative true, probability of defective is 15%. So that means the binomial distribution in a sample of 10 and probability equal to 15% on each trial is less than or equal to 1 is 54.9% of a type 1 error. Type 2 error. And for practical significance, that means that we would fail to reject H0, meaning that we conclude that the portion of defectives is 10%, when in fact it is 15%. That's pretty bad. So over half the time, you would be subject to this type 2 error with this random decision. Okay. So of course there are ways to fix this type 2 error. In this specific setting, you could have a larger sample size that would greatly help in these things. Okay. And that's really the main thing that you could be used. But inspecting parts is rather time consuming and costly. Now, one last thing I want to go over is just a case study in R, since that's how you would probably analyze a lot of these things. And like I said, the most common way to test hypotheses is with the t-test, the t-distribution. But all of these other scenarios arise, and I want you to be aware of them. Okay, so here's a case study in R. And the question is, are any psychological indicators associated with schizophrenia? And so in 1990, researchers reported the results of a study that controlled for genetic and socioeconomic differences by examining 15 pairs of monozygotic twins, where one twin was schizophrenic and the other one was not. And the researchers measured the volumes of their brains. Okay, so here's what the data looks like. This is a real study. There's a non-schizophrenic twin, the unaffected, and this is the brain size. Then there's the affected twin, and here's their brain size. I calculated the difference. Why is taking the difference a good thing? Well, this is a specific example of what's called a match pair experiment, in which each unit in the affected has a natural comparison to the unaffected. So that is, they're birthed from the same person, they're raised in the same household. It's accounting for genetic differences. So among the two twins, socioeconomic differences, and a whole slew of other what's called confounders, things that could affect brain size. Okay. The difference is what we use to test the population mean. Difference is 0. So if the difference, the mean difference is 0, that would mean the population mean of the unaffected, non-schizophrenic, is equal to the population mean brain size of the affected. Population mean of the affected, the schizophrenic, is equal to the population mean of the unaffected, i.e. the unschizophrenic. So here's the math. This test of hypothesis is what we're performing. We're calculating the difference and taking the sample mean. And what it's really doing is it's equivalent to this, these two, comparing the two population means. Okay. Well, there are more reasons for taking the difference. I discussed this one first, is that helps account for confounding variables. The t-test requires that the observations be independent and identically distributed. The observations of the non-schizophrenic are not independent of the affected, the schizophrenic. So after all, they are correlated. They're twins, so there's going to be correlations among their observations. But the difference is independent because it's the difference within households, okay, within the twins. The assumption of identical distribution is false, as the mean brain size of the unaffected is believed to be different from the affected. However, the difference is identically distributed here. Okay, and then if I want to perform this in R, it's in the statistical sleuth, case 0202, and I calculate a difference via this. Then I can run the t-test in R with that command, and this is the output. Okay, the p-value, the level of alpha associated with this test, And remember, the p-value is the level of alpha, is less than 1%, is 0.006. And so that's overwhelming evidence that there is a difference. The mean difference is 0.19 cubic centimeters. So if you're not schizophrenic, you have a brain size that is 0.19 cubic centimeters larger on average. Not true on every single observation. Okay, so next I take these results and I parse them just into a couple of bullet points. So the p-value, that's the level of alpha, is less than 1.1%. I'm calling that clear evidence, but it's a bit of philosophical speak. Clear is different from everyone, but most people would agree that the odds of something occurring less than 1% is pretty strong evidence that the mean difference in brain size is not equal. Is estimated that there's a 0.19 cubic centimeter difference, and the 95% confidence interval, right? Every time I take a different sample, I'll get a different result. There's only 15 individuals in this. Ideally, there should be 30. So that's one downfall of this study. But if you examine the assumptions, the 15 data points obey a lot of statistical properties that make this really nice. Okay. The 95% confidence interval is a kind of a measure of variability and the difference that you might expect. So instead of it always being equal to 0.19 cubic centimeters, it's saying, well, there's some variability in the samples. It could be 0.33 to 0.06, and this is kind of using this how most people interpret confidence interval, but the correct term is that 95% of the time the confidence interval contains the mean, and that interval ranges from 0.06 to 0.33, but in most executive meetings, you're going to report this. Okay. So thank you for watching. That's all I have on hypothesis testing from Chapter 8. Thank you.